Thank you, Ms. Chairman, for your gracious invitation. Hello, everyone. I'm honored to have the chance to address my paper on this special occasion. The topic of my paper is Predicting Congestion Attack, a variable spoofing frequency for reliable traffic signal system. The outline of my talk is as follows. In the first part, I want to introduce the background of this research. The second part suggests a model that predicts the congestion attack on the different spoofing frequencies for a reliable traffic signal system. The third part covers the experimental process and the empirical results. Finally, a simple conclusion is given. As a key component of next-generation transportation systems, the intelligent traffic signal system is designed to perform dynamic and optimal signal control. The U.S. DOT has sponsored a kind of such system, Yike, based on controlled optimization of physics. Yike systems are currently under testing in some USA states. As shown in the left figure, the Yike system contains three main parts. OBUs, onboard units, are hardware devices deployed on connected vehicles. RSUs, roadside units, are responsible for receiving and maintaining BSM messages to broadcast. The traffic signal controller receives signal control commands and then executes them. The right figure shows an 8-phase intersection and data flow of the Yike system. Each OBU of vehicles sends BSM message to the RSU for a trajectory collection in real time. Such data will then be pre-processed to form an arrival table as an input to signal planning with COP and EVLS modules. If the penetration rate PR of OBU for vehicles is below 95%, the arrival table will be sent to the EVLS algorithm for an update. The EVLS algorithm will estimate the trajectory data of the unequipped vehicles. Otherwise, it will be sent directly to COP for planning. According to the results of COP, a downward signaling command is transferred to the phase signal controller. After each stage of signal control, the following signal states is returned as feedback for continuous COP planning. Unfortunately, there is a severe security problem with Yike, which is revealed by Chen in NDSS 2018. A congestion attack can be launched via data spoofing of one attack vehicle. Due to the vulnerability of COP algorithm, attackers can compromise the OBU on their vehicles and send malicious messages such as speed and location, which can affect the traffic control decisions at proper timing and cause unexpected heavy traffic congestion. The right figure shows the congestion attack results. One single attack vehicle can cause more than 11 times the total delay, which significantly hinders the development and feature large-scale deployment. As shown in the left figure, there are two attack strategies of data spoofing proposed in ASIC. The first strategy, arrival time and phase spoofing, applies to both full deployment and transition periods. The attack alters the arrival time of the vehicle and its request phase by changing the location and speed information in the vehicle's BSM message, thus changing the corresponding arrival table elements. This attack strategy can directly attack input data flow, regardless of PR. The second strategy is queue line spoofing, which only works during the transition period. The purpose of this strategy is to extend the queue lines estimated by EVLS algorithm through changing the location speed values in the BSM message. Since the EVLS algorithm estimates the queue lines based on the location of the last stopped connected vehicle, this attack results in an increase in the estimated queue lines and the number of vehicles in queue. Therefore, the objective of our research is to propose a prediction approach of a traffic congestion attack, which can recognize the abnormal congestion and attack frequency and timely predict the forthcoming congestion attack. For the highlights of our research, we are the first to study traffic congestion attack and under various frequencies in the ASIC system in order to predict the subsequent congestion attack based on solid feature engineering and spatial learning tricks. We proposed a unified example learning framework to perform supervised classification tasks. We evaluate our approach from an actual COP algorithm through VSIM. Let's move to the theoretical model of our research. We propose a unified example learning-based framework for binary classification and multi-class classification on ASIC traffic flow. We define some features which are related to congestion attack. The definition is as follows. The vehicle capacity ratio is the ratio of total vehicle number of all its phases to the vehicle capacity of all its phases. Congestion degree is the ratio of the vehicle number of queuing to the vehicle number of normal queuing. Attack accelerate is the acceleration of capacity ratio and congestion degree at moment t. Attack amplification ratio is the amplification ratio of capacity ratio and congestion degree at moment t. As shown in this table, according to whether it is for the whole intersection or a specific face, features are divided into macro features and micro features. And we sample the first 10 times of flow head and the last 10 times of flow tail to construct training samples. As this figure shows, there are 3 parts: pre-processing, training set, and example learning. In pre-processing, we extract features from the collected traffic flow of the ASIC system. Next, we use standardization, a kind of rescaling trick, to adjust feature values. Furthermore, through labeling, we separate 2 datasets, D1 and D2, for binary classification and multi-classification, respectively. To ensure a balanced sample dataset, we also utilize smooth oversampling trick. Example learning is the core component of this framework. It involves complete example learning methods, including bagging, boosting, and stacking, and research trick. We choose 4 basic learner types: DT, SVM, LR, and KNN. For each class, we train 10 basic learners. Bagging and boosting are used for learners of the same type, while stacking is used for heterogeneous learners. The framework is designed for comprehensive supervised learning to discover patterns of traffic flow for both general and each frequency-specified congestion attack. Here we show the experimental setup and process and list the experimental results to demonstrate the superiority of our method. The experimental environment and sample datasets configuration are shown in the table. For the experiment process, we first collect a period of primary traffic flow data and convert it into form of features we defined. Then, the example learning model trained on this dataset D1 can distinguish whether the congestion attack is occurring or not after inputting the converted traffic data. And if the prediction result of step 2 is attack, the attack frequency can be output by the example learning model trained on dataset D2, and then compare the appearing frequency of vehicles at the road junction with the attack frequency detected at step 3. The congestion attack vehicles are found if FV is around 2 FE. Then the discovery of attack vehicles can help the defense of ASIC against traffic congestion attack. We carry out experiments for different approach on the different traffic flow feature sites. As shown in this table, the accuracy values of SARMA, TGRU, and EL on the feature set. Our approach has the best accuracy value, which demonstrates that our approach is superior to others from the perspective of the feature set. The accuracy value of each approach on the feature set FS3 is higher than on other feature sets. That indicates the effectiveness of our defined traffic flow features. We evaluate accuracy of 6 feature compositions and even the full composition scheme, as Table 6 shows for bagging, Table 7 for boosting, Table 8 for stacking. The both show that the ensemble classification has satisfying accuracy, and in practice, we recommend CR or the set of CR, alpha CR, beta CR for efficiency. Here we choose CR as the only feature in this comparison. Table 9 and Table 10 report the accuracy comparison without and with grid research respectively. We also give the training time of different example learning in Table 11, and we can see that bagging is more efficient. Besides, AUC is used to compare bagging with boosting. As Figure 4 shows, there is only a little difference between bagging and boosting. For D1, D2, we draw decision trees respectively to characterize explainable patterns. We can find that these patterns are relatively clear and operable. The patterns of different classes are counted in Table 12, and we can infer the classes from the given sample data. At the last, I'll give a conclusion for our research. We propose a novel approach for congestion attack prediction. We implement example learning to build correlations between abnormal congestion and attack frequency. Based on supervised learning of historical data, we can recognize the current attack frequency and further realize the prediction of the subsequent congestion attack. And finally, the experimental results have shown that the superiority of our approach. Well, that's all for this presentation. Thank you for watching.